All right, guys, I think this is hopefully the last round of practice problems that we'll be doing on Lewis structures here. So let's give it a go. All right, I wanted to do ClF3. Chlorine is a halogen, 7 valence electrons. Fluorine is a halogen, 7 valence electrons. There's 3 of them. That's going to be 28 valence electrons. 7 plus 7 plus 3 is the same as 7 times 4, which is 28. Chlorine is less electronegative than fluorine. Fluorine's the most electronegative element. So we're going to get something like this, right, with chlorine in the center. Give an octet to the fluorines by adding 6 non-bonding electrons, 3 lone pairs, 2, 4, 6, 8 for each of the fluorines. And so each of the fluorines has 8 with 3 of them. So we have 24 electrons accounted for, but we have 28 valence electrons. So we need to add 4 more electrons. And where are we going to add them? On the chlorine. How many? Because that's all we can do is on the central atom. That's all we can do. If you have too many electrons, a double bond actually will hurt you. Okay, double bonds only, or triple bond only when you're deficient. You know, you have not enough electrons. But if you have too many, you're going to violate the octet rule, and you're going to make a expanded octet. And so that's what happens here. Chlorine has 2, 4, 6, 8, 10. But again, chlorine's in the third row, so we're allowed to violate the octet rule if we have to. Okay. Next one I wanted to do was CH3COO minus. So kind of a bigger one, but fundamentally everything's the same here. Let's see. We have this is actually acetate. It's the ion of acetic acid, which is what vinegar is. Okay, vinegar is 5% acetic acid in water. This is approximately. This is carbon worth 4 valence electrons. We have 3 hydrogens worth 1 each. Then we have another carbon, and then we have 2 oxygens written out in the structure, plus minus 1 charge. So that's going to be the 1 more electron there. So 4 plus 3 is 7, plus 4 is 11, 17, 23. That's going to get me 24 valence electrons in the whole structure. All right, so what do we do here? Well, we have 2 carbons. And generally when you have, this is getting into organic chemistry, so we're not going to do a lot of this in this course, but generally when you have more than 1 carbon and you have a lot of other atoms, you're going to put the 2 carbons next to one another, okay? Carbon, you know, you've heard is like the backbone of life, and it's carbon chains that are linked together that form a lot of organic compounds that, you know, form the basis of biology as we know it. And so we're going to put 2 carbons together. And then one of the carbons has the hydrogens that are around it, right? And then the other one has the oxygens that are around it. And so our framework is going to look something like this. Okay, and now we have to figure out the octet rule and stuff. Well, the hydrogens are good. They're the duet rule. They all have 2. So hydrogens, we're going to leave those alone. This carbon is actually good because look, it has 2, 4, 6, 8. Okay. This carbon's not good. It has 2, 4, 6. So that's going to need to be fixed. And total number of valence electrons we have is what? 2, 4, 6, 8, 10, 12. We have 12 counted for, and we have 24 total. So we're going to have to add 12 more. Well, I want to fix this carbon first. It has 6 valence electrons. So I want to help it out either with a lone pair or with a double bond. And so let's just go ahead and add a lone pair to start out. And then, so that brought me up to a total of 2, 4, 6, 8, 10, 12, 14. Now I'm going to keep adding up to 24. So as that distributing them equally across the oxygens, I was at 14. I need to get to 24. And so that's going to be 16, 18, 20, 22, and 24. Okay, so now I can look at what's going on here. Oxygen here is what? 2, 4, 6, 8. That's octet rule's good. Carbon, octet rule's good. 2, 4, 6, 8. Oxygen here, 2, 4, 6. That's bad. So that's telling me I'm going to have to take this lone pair on the carbon, and I'm going to have to change that, erase that one, and change that into a double bond here. Okay? And that then makes this fine. 2, 4, 6, 8, and the carbon's still fine, 2, 4, 6, 8, okay? This oxygen we didn't change. This is a -1 charge, so I'm gonna put a bracket and a negative sign. Now, hopefully you can see that I could have done the same thing on this oxygen. So there's gonna be an equally valid resonance structure, and all the formal charges are gonna end up being the same because we just are switching the position of this double bond. And so that resonance structure is gonna look like this, where all I'm gonna do is this CH3 part is gonna be the same, but I'm just gonna put the double bond here, okay? And I'm gonna put my bracket, and then I'm gonna put my single bonded oxygen. Oops, that looks a little weird. Gonna put my single bonded oxygen right there. And so those are equally valid. They're essentially the same resonance structures. All the, we don't have to use formal rules, formal charges here to distinguish between them because they're all, types are similar. Here, this oxygen is the same as this oxygen, and this oxygen double bond is the same as this oxygen. So they're going to be the same, and the bonding here would be intermediate between a double bond and a single bond. So last question I wanted to go over is this one. It says, which of the following is the best Lewis structure for HNO2? That, by the way, remember your naming rules. That's nitrous acid. This is the nitrite anion. You would use your formula sheet to know that. So which is the best structure? Well, first you want to make sure octet rule is in place here if we can. So here, let's see, 2, 4, 6, 8, good. 2, 4, 6, 8, good. 2, 4, 6, 8, duet for hydrogen, good. 2, 4, 6, 8, good. Nitrogen, 2, 4, 6, 8, 10. I don't like that one, okay, because it has 10. It violated octet rule. Here, nitrogen, 2, 4, 6, no. Okay, violated octet rule. Here, 2, 4, 6, 8, 2, 4, 6, no. Okay, so based on that, it's going to be number 1, and we just figured that out using the octet rule. All right, guys, so we made it through all those problems. That was good. Keep practicing them on your own, and you'll be fine on this type of stuff. It's not intrinsically too hard. There are a lot of things to keep track of, but if you practice it, it's actually very different from the other problem solving we're doing, right? Which was more math heavy. This is more graphical, and so I think a lot of you will do quite well in this. All right, take care.